It's really a great pleasure for me to be here, to be part of this course, IOCCG third course, and have the opportunity to provide the first lecture of the course. I would like to thank very much David, all organizers of IOCCG, everybody who made contribution and make this event be as it is, and also, of course, including sponsors. And I wish you enjoyable time, great 2 weeks in Villefranche, and I hope this experience here will have very positive and good impact on your lives and on your career. And I must say that this is really a very, very unique place, Villefranche-sur-Mer, and this Oceanographic Center laboratories with great traditions, great history of research in ocean optics, ocean color remote sensing. I would be remiss if I didn't mention late André Morel here at this point, as you probably all know, his great contributions to this field, and many others who were his students and visitors, postdocs, and contributed to this field enormously. And this is unique place, so it's the best I can tell you. So you're in the right place, the right time, and hopefully this experience will have great impact on your lives. As it had, in fact, on my own, I would like to share one little story of mine. I was, like many of you, at your stage of career and your life. 30 years ago, in '96, I came here shortly after completing my PhD in Poland. I spent 2 years of my postdoctoral research here, and it did really impact my life and in a very great way. So the topic of my first lecture today is basically introduction to physics of light. And I would like to talk a little bit about things like the nature, what is light, address the questions, what is light, and how light interacts with matter. And we decided, I think, shortly after the last course 2 years ago, that it would be useful to have some introductory lecture on the basic physics of light. And I believe that for many of you, it will be a review of things that you know very well from courses in physics, courses in electromagnetics. Maybe hopefully for some of you, this review, for those of you who know this stuff very well, will be still useful. And for those of you who haven't perhaps had the opportunity to learn about these things, it will provide you at least good physical intuition about light and about interactions of light with matter, and which will be helpful for whatever you do in the field of applications of ocean color research and ocean optics research. So, as you know, my name is Dariusz Stramski, and since '97 I've been with Scripps Institution of Oceanography, where I founded an ocean optics research lab. And just a few words about my own work. It covers a very broad range of topics in ocean optics, ocean color remote sensing, from fundamental research on interactions of light with seawater constituents, especially particles, different types of particles. We do all kinds of field observations in support of ocean color research and other work in ocean optics, development of algorithms for remote sensing, and also all kinds of work in the area of theoretical modeling, including radiative transfer modeling, or modeling of interactions of light with matter. So let's go back to our first question that we'd like to talk about. And this question is, what is light? And I decided to start with this citation from Albert Einstein. Every physicist thinks he knows what a photon is. I spent my life to find out what a photon is, and I still don't know it. So on one hand, you know, it tells us that it's a very complex question, even though it may seemingly be a simple question. It's not easy to answer this question. But on the other hand, if I don't succeed during this lecture to answer this question, I will feel better just based on this, what Albert Einstein said. So, and the way I will approach discussing the nature of light and interaction, the mechanism of how light interacts with matter, will be in a very general, conceptual, and descriptive manner. It's not going to be very rigorous, but hopefully it will provide physical intuition and understanding, so it will provide a good basis for other work that you do. And we'll try to maybe follow this idea that physics should be made as simple as possible, but no simpler, within the constraints of 1.5 hour of our lecture. We'll try to talk about light and interactions. So let's begin with classical physics. How classical physics describes light. It describes this as a wave that consists of coupled electric and magnetic fields, which are here depicted in this picture as vectors. So there's electric vector and magnetic vector perpendicular to it, and the wave propagates in the direction that is perpendicular to both electric and magnetic fields. So there's, as any wave, it is characterized by a series of properties: wavelength, frequency. An electromagnetic wave also carries energy. So we will talk a little bit about that. And very importantly, as you can see from this diagram, it is also a transverse wave. It means that the field itself oscillates in the direction perpendicular to the propagation of the wave. And we'll talk about the sources, where it comes from, and so on and so forth. But once it is produced, electromagnetic disturbance, the two fields that oscillate in unison, in synchrony with each other, it is unleashed of its source and propagates through space, through free space or material media with incredible speed, with a phase speed of about 300 kilometers a second. So I have two slides about basic laws of electromagnetism from classical physics. The first is will remind us about the forces, force equations, how fields affect charges. So we're here, if we have a point charge with an electric field, it would experience an electric force, Fe, which is basically defined here as F, and the vector F. This is electric force, Q is the charge, and E is the magnitude of the electric field. And any moving charge may experience, in addition to electric field, electric force may experience another force that is proportional to its velocity, V, and this would be a magnetic force. So it's also often called the Lorentz force. Sometimes the Lorentz force is basically also called as the combination of both electric force and the magnetic force. So basically what this tells us that the magnetic force tends to deflect the charge as it moves through the magnetic field. And we have a vector product of the velocity of the charge and the magnetic. So of course, if the vector product, so if they are in parallel, it's zero, right? There's no deflection, because sine of 0 degrees is 0. So this is the one set of basic laws of electromagnetism. Another one is about the question of how charges produce fields, or how fields are produced in more general. So electric fields are generated by electric charges. So whenever you have electric charge, it will generate an electric field around this charge. And there's also another way of generating electric fields. It turns out that time-varying magnetic fields generate electric field as well. And magnetic fields are generated by charges in motion. So whenever we have charge in motion, we generate a magnetic field. An example would be electric currents, or the most fundamental example of generation of magnetic fields through the motion of charges would be a spinning electron within the atom. And also time-varying electric fields are sources of magnetic fields. And all these phenomena here have been put together in 19th century by James Clerk Maxwell into 4 equations. So actually these 4 phenomena are most of these phenomena have been already known when Maxwell was working on his famous 4 equations. Nevertheless, he added one component to one of his 4 equations. We don't really have to go during the scope of this course to all these details, but I just want to make some major points about these equations. And so without going to really to mathematical details about how they look like, and there are 4 equations in the integral form. There are also equations, Maxwell equations, in the differential form, which explain all these phenomena that were in the previous slide. But basically, I would like to show one thing here, which was a great achievement of physics, of classical physics of 19th century. when Maxwell put all these equations together and did some math with it, and assuming that the wave propagates within a free space, he rewrote these equations in this differential form for free space. He obtained two equations like this, where mu sub-zero and epsilon sub-zero are just basic physical constants, magnetic constants and electric constant for free space. These numbers were known at the time of Maxwell. So this is Laplacian operator. And these are vectorial equations, so you can write each of these equations in terms of three scalar equations for each component x, y, z of electric field and magnetic field. And this is just an example of one of 6 scalar equations for the x component of the vector E. And when you write this equation, and he did it, he found that this equation has a very familiar form. It has a form of wave equation that has also been known at the time. And it would be a wave equation under the condition when the product of these two physical constants was 1 over squared phase velocity of the wave. And it turns out that these two physical constants were known when he wrote this and when he derived these equations. And the velocity, phase velocity of electromagnetic waves were known with pretty good accuracy in the middle of 19th century. When he put it together, it turned out that this equation is satisfied. So it basically was an evidence that light on electromagnetic, that light is an electromagnetic radiation. So this was an enormous achievement that was made by Maxwell. And there are several important derivations that were also made from Maxwell equations. One is that these electromagnetic waves are transverse, so that you can also derive it in a very elegant mathematical way from his equations. Another thing coming out of this theory is that energy is being transported by electromagnetic wave, and it is being quantified by the so-called Poynting vector, which tells us how much energy is being transported by electromagnetic wave per unit time per unit area. And so this is a Poynting vector. Instantaneous value of Poynting vector is proportional to the vector product of instantaneous values of the electric and magnetic fields. And you can write it in different forms, but the bottom line is this product. And important thing is that in the range of frequencies that we are dealing with within the electromagnetic spectrum in terms of visible light, these fields vary very, very rapidly. Yes, they vary like 10 to 14 times per second or so. 10 to 14 to the power 14. Yes, so that's very rapid changes, which are not practical to measure. So, in fact, later on during the course, you will have lectures on radiometry or radiometric quantities, what we typically deal with in oceanic optics, the things like radiance, irradiance, and so on and so forth. You've seen this instrument, some of you at least made these measurements. So really what you measure is something like this, is a time average Poynting vector. Yes, so radiance, irradiance, or radiance meters, depending whether you collect large different directions or maybe single direction, different radiometric quantities. But basically what you're doing is the time averaging this over very many cycles of electromagnetic wave. So the time average magnitude of Poynting vector, it provides us a bridge between classical physics, electromagnetic theory of physics, and radiometry. That's the bridge. And it's proportional, by the way, it's very important, it's proportional to the square amplitude of the electric field. Yes, so what we are measuring, really, irradiance, the magnitude of irradiance is proportional to the squared amplitude of the electric field. Okay, and now I have a series of slides that will tell us a little bit about the history. It's very interesting. That provides additional evidence about wave properties of light. So we are still in the realm of domain of the classical physics when we are talking about one type of interpretation of what light is. And it's a wave-like property, right? So the English physicist at the beginning of Thomas Young, at the beginning of 19th century, he made this famous double-slit interference experiment. That's how it is called, where you pass light through the two slits and observe this pattern of fringes, interference fringes, in the far field on the screen. And basically, this phenomenon cannot be explained unless light is considered as a wave, because each of these slits are considered as point sources of spherical waves. And if you basically construct interference pattern from these two sources, you get these fringes with maxima and minima, so constructive, destructive interference, and so on and so forth. So the Young's experiment was basically the one that provided an important experimental evidence about wave-like nature of radiation of light. And before I go to the next one, I should say that, as you have probably noticed, I didn't mention anything about specificity of Maxwell equations with respect to frequency or wavelength. So they apply throughout the entire spectrum of possible frequencies and wavelengths. That's a very important aspect. We'll get to this. This is basically the manifestation of the so-called electromagnetic spectrum. And in free space, these equations I showed hold for any frequency, right? They're independent on frequency. It means in free space, electromagnetic perturbation, or wave if you wish, regardless of frequency, will propagate with the same phase velocity in free space, in vacuum. This is not true in material media. We'll touch upon this aspect as well. Okay, so at the end of 19th century, beginning of 20th century, the Maxwell electromagnetic theory and explanation about electromagnetic waves enjoyed enormous success and was supported widely. But there were still some phenomena that were observed that were difficult to explain in terms of wave theory. And one of them was the so-called blackbody radiation. Max Planck worked on that. And another one was the so-called photoelectric effect that Albert Einstein was working on 1905. He published one of his 4 papers in 1905. It was an amazing year. It's referred to as Annus Mirabilis, miracle year. Albert Einstein published 4 papers in 1905 in Annalen der Physik in German. The first one was on photoelectric effect. I don't know if you're familiar with the 3 other famous papers. The second one was on a molecular kinetic theory, in which he explained the Brownian motion, interaction of molecules with small particles, and interaction of molecules in thermal motion, interacting with particles and producing Brownian motion. The third paper was his special relativity paper, and the fourth paper, probably one of the famous of all, equivalence of mass and energy, right? 4 papers in one single year. But we're going to talk about the first one. The title of this, after translation to English, on a heuristic viewpoint concerning the production and transformation of light. And in this paper, Einstein explained the phenomenon in which when you bombard a metal electrode with a beam of light, you may observe a phenomenon which consists of electrons being ejected from the metal itself. And it was interesting to observe that you can bombard, for example, potassium with red light, and no matter how intense red light beam is, nothing happens. No electrons are being ejected. It can be weak and with very strong intensity. There's no electrons are ejected. But when you bombard it with blue light, for example, or violet light, you observe ejections of electrons from this. And that led him to believe, Even if you put a weak beam of light intensity, you can observe that. So that led him to believe that light behaves like particle-like entities, that energy is concentrated within discrete packets, and which he referred to as photons. I don't know if that really comes from his paper, the name of photon, or not. Probably
later, like
late
1930 or something.
1930, yeah. So this actually is a later concept, the name itself, but nevertheless, the bottom line is that you need, and the idea is here that the different colors, if you wish, or different frequencies or wavelengths, these packets carry different energies in terms of quantized amounts of small quantized amount of energies that are sufficient to deliver energy to an atom, enough energy that electron can leave the atom, can be ejected. So this was called photoelectric effect. In fact, Einstein received 1921 Nobel Prize for his overall contributions to physics, but with emphasis on this particular paper. This paper has been emphasized when he received this Nobel Prize as a specific work of his that contributed to the Nobel Prize. And here is an interesting slide I came across some not so long time ago on internet, and I would encourage you to do something, to go to this site. If you can read it, I can tell you, maybe as a homework tonight, if you have time, 10 minutes, to watch this movie. It's a great movie. It's basically an experiment that was done in 1980s by Hamamatsu Photonics about something like they intended to repeat something like a Young's double-slit interference experiment using novel technology of detection, some very sensitive camera that actually respond to very small amounts of quantized energy hitting different portions of the sensitive area of the camera. And they basically did this. If you send a very strong beam of light on that system, on this detecting system, you see very many signals in different sensitive areas show very many dots. But the idea was, what will happen if we start decreasing intensity of the beam? Assuming that we know that light possesses the particle-like nature, that we have discrete packets of energy, quanta, what's going to happen if we send this, and actually this was sent through a double slit, yes? We still have double slit. And they are decreasing amounts of intensity. The intensity of beam is being decreased. And what they are observing, and if they look at the signal over a short period of time, nothing interesting happens. There is like a scattered image of dots. These are hits, individual hits of photons on the sensitive area. But if they observe for a long period of time, very, very weak signal. This could be even individual photons. This camera is so sensitive. You could just put the light so low that you have just single photon going on. But if you observe for a very, very long time, you start seeing something like this. Signal strong, constructive interference, destructive, constructive, destructive, and so on and so forth. This is one of the first, probably the first ever, at least to my knowledge, experimental proof that single photon can interfere with itself. So this is yet another beautiful evidence that light has the dual nature, because in the classical Young experiment, you see something like this. And with very, very low intensity single photons, you see the same effect, more or less the same pattern. So this experiment captured the dual nature of the photon by a special camera for the first time ever. That at least what Hamamatsu is claiming. But I encourage you to look at this. It's a really nice thing. Okay, so we come to the conclusion that light has both, has a dual nature. It seems to be a wave. It seems to be a particle. So it is likely neither. But certainly most phenomena can be successfully explained when we refer solely to classical, in terms of classical physics and electromagnetic waves. We can use it, and we can be fully satisfied with using this description. In some, of course, if you go to modern quantum physics and the light is really described and electromagnetic radiation or perturbation described in terms of quantum electrodynamics, that's the fully rigorous theory. So let's talk about here. I didn't find any other or any better graphical representation how we can graphically represent photons or these quantized portions of electromagnetic energy propagating through media. Well, I found something like this. It's probably not satisfactory, but this is not important. What's important is here that in this slide we are summarizing several important properties of photons. The energy of single photon is proportional to frequency, where h is the Planck's constant. So it is also proportional to, inversely proportional to wavelength, where c is the phase velocity. These are the values for Planck's constant. And this is the phase velocity in free space, independent on lambda. What's very important for us when we are doing work in water in the ocean is really to realize that how this thing, how we can rewrite this equation for a photon penetrating from a free space or atmosphere, which is pretty close to free space in terms of its refractive index. By the way, refractive index is related to phase velocity. But when a photon propagates from, let's say, atmosphere into the ocean, what's going to happen? What kind of properties are going to stay constant? Let's say there is no losses at the surface due to reflection. So the energy is being conserved. The Q stays the same. The frequency stays the same. Yes? So what has to change is this in synchrony. C and lambda has to change to the same extent to satisfy the conservation of energy. So this is written here. Phase velocity in water would be C over refractive index of water. I omitted lambda for the sake of simplicity, but this now will be a function of lambda. So this will be a dispersive medium to some extent, that phase velocity in any material medium is a function of lambda and frequency. And refractive index of water for within this electromagnetic range of spectrum that we are interested in varies within a relatively small range, 1.34 or so. So this ratio is, so it's dropping, the velocity, phase velocity is dropping by about 25%. And the energy of photons stays constant, so lambda has to also be shorter. This is important to remember because you will read, tens, hundreds of papers and books in oceanic optics. You will almost always, you will have lambda, which relates to free space, even though we're talking about radiation in water. So it's important to know that for the sake of simplicity, we always keep it simple and relate to lambda in free space rather than in water. It turns out that in our field, we like to use lambdas rather than frequency. If we used frequencies, wouldn't be a problem, right? But it would be invariant with respect to the medium. But in terms of lambda, it is. But lambda is convenient because we are operating from a few hundreds of nanometers to maybe thousands of nanometers or so. Okay, so this way I am coming to the concept of electromagnetic photon spectrum. It's a continuum going from so we have here the axis is increasing wavelength. The opposite direction is increasing energy, yes, energy proportional to frequency or inverse proportional to wavelength. So we're starting with extremely short wavelengths, high frequencies, gamma rays, X-rays, UV, very narrow range, visible range, from about 400 to 700, infrared, radio waves, and so on. Another illustration, I'm not going to go through these details, but if you have access, I believe you will have access to all these slides. So this would be for your reference. You have here electromagnetic spectrum. This axis is frequency, from high frequencies to low frequencies. It's a little bit hard to read probably, but it's also a reference here. This is textbooks in physics. Wavelength, photon energy in joules, electron volts. So here's the visible range light. And you also have microscopic sources. So we see that in the light, this is mostly related with some interactions, or something happens within the outer layer of electrons within atoms and molecules. We'll talk about this a little bit more in a moment. In the infrared, we see vibrations, rotations. We'll talk about this as well in a moment. Detection, different ways of detecting radiation in different areas of electromagnetic spectrum. Also artificial generation here. Okay, so but things are even more complex if you think about the possibility of orientation of oscillating electric vector with respect to different planes. I mean, when you have electromagnetic or the torrents of photons propagating, or electromagnetic wave propagating, and if you were able to observe instantaneous electric field in the beam of light going from the sun, it would be basically unpolarized, meaning that there is no favorable plane within which the electric field oscillates. It changes randomly. So this is meant to show it. You would be observer here, you would see in one instant of time it's oscillating like this, then here, then there, and there is no predominant direction or plane, if you wish, in the so-called randomly polarized beam. And this is the beam that is produced, at least this is how we understand it's produced by sun. But the interaction, when the randomly polarized beam, or oftentimes called unpolarized beam, goes through material media, through interactions with material media, it can get polarized, or partially polarized, or fully polarized. It means that the electric field will behave in some orderly fashion. So over many cycles of oscillation, it will have some orderly or certain specific pattern of oscillations. And the simple one is like this. It's linearly polarized light, and it can be linearly polarized with different planes, or it can be circular polarized. So if we are observer here and the beam is coming towards us, if we are able to observe instantaneous positions of the electric field, it would basically move around this circle like that. Or that would be right circular polarization, left circular polarization. If the magnitude of this vector is different, it could be elliptically polarized light and things like that. I don't really have time to go through presentation of how it is. But the easiest way to explain the circular polarization is imagine that any beam of light in which you have electric vector, resultant net electric field can be represented in terms of two components, two orthogonal components, and if this beam of light propagates through some medium in which one component is moving slower than the other one is vibrating like this, another one like that. They move through some crystal, for example. One is being delayed, and they can produce circular polarization. If there is a specific delay one component versus the other. In fact, 90 degrees, yes, 1/4 of the wave cycle if you have the so-called quarter wave polarizer can produce something like this. The linear polarization is easy to produce from randomly polarized beam. You can purchase filters for, I don't know, several dollars or something like this, probably some devices that basically some filters that these are the polymer molecules that are oriented in a specific way, and they can when molecules in the filter, for example, are aligned vertically here, the polarization axis is horizontal because this component is being fully absorbed. Only that component propagates through the filter, and vice versa here. When molecules in the filter are aligned horizontally, polarization axis is vertical. So that component is fully absorbed. So okay, I just wanted to mention about this, that that polarization is yet another property of electromagnetic radiation. And light becomes partially polarized as it propagates through the atmosphere and is partially polarized within the ocean. So polarization can occur through transmission, as you have seen on that previous slide, but it can also occur through scattering. So when randomly polarized beam hits a particle or small molecule, it can get polarized, and the strongest polarization degree of polarization is at the scattering angle at 90 degrees. Basically what happens is the component that the electric vector component along this axis vanishes. Yes, and that satisfies also the requirement that the wave has to be transverse. So for very tiny molecules, isotropic molecules that have isotropic electromagnetic properties, the light that is being scattered at 90 degrees would be fully polarized in vertical directions, where the plane of reference is the plane that contains the incident beam and the scattered beam. That's our plane of reference, so it's vertical to that plane. Polarization can also occur during the process of reflection, and that's important when light coming from the atmosphere interacts with water surface. So at a certain angle, there will be a significant degree of polarization. This angle is referred to as Brewster angle. And I'm not sure, I might have a little bit of time to talk more about that in a moment. Okay, so a few other things about wave nature of light, some other phenomena that can be nicely explained by using the classical physics and the wave properties of light, and the reflection at the boundary between two media of different densities of refractive index can be nicely explained using the wave description of light. And it actually dates back to 17th century when this Danish scientist Christian Huygens presented his theory. He was actually the one who postulated that light is a wave. So long before Maxwell, but he was not fully correct on many aspects of it. But nevertheless, he had some important concepts that we can use today for explaining some phenomena such as reflection. He actually postulated that light is a longitudinal wave, so like acoustic waves. So the oscillations are within the direction of propagation, which is not true. But one interesting concept that he introduced was this. He imagined that this is plane parallel wave. Yes, so this is, let's say, this is a crest, this is a trough. Yes. So these are wave fronts here, propagating towards let's say this is atmosphere, this is ocean. So this is our boundary. He postulated that each point of the wavefront here can be considered as a source of spherical waves. He didn't explain why these spherical waves propagate only in that direction. He assumed in his description that the spherical waves propagate only this way. As these spherical waves, very many spherical waves from each point are generated, and they create the next wavefront, and so on and so forth. So that's the principle. That's referred to as Huygens principle. And you can also use this concept when you look at the interaction with the boundary here. When the wavefront, this point of the wavefront hits the boundary, this point generates the spherical wave, and then a moment later, this point generates spherical, this wavefront, this portion of the wavefront touches this point, and so on. After some period of time, this portion of the wavefront gets to here. So by that time that this point, this part from B gets to D, this already is at this point. So the reflection, so you can see you create a new wavefront of the reflected wave that goes this way. That's actually is shown here. These are supposed to be wavefronts of the spherical wavefronts that interfere and create a new wavefront, CD from AB. So we are in the same medium, yes? So it takes the same amount of time from B to D as from A to C, yes? So that tells us that the angle of incidence, which is measured between normal and the direction of incidence, is the same as the angle of reflection. Very important reflection law. Now we are looking what happens with. We still can apply Huygens principle and the generation of the spherical spherical waves that generate, after interference, generate wavefronts. But we are now in a medium with higher refractive index. So in fact, what you see is actually the wave refracts, changes direction from this direction to this direction. And just the time it takes to get to here, this point, it goes much faster here than there, right? So this is a shorter distance than the distance there. This distance is longer than this distance. So that's why wave refracts. Some of the consequences of refraction, for example, if you are underwater and observe and look up, or actually if you're observer above water, so you may see at some apparent position underwater objects, which is shown here. It works both ways. Of course, if you go from the medium with higher index of refraction, like water, into lower index of refraction, so that nothing happens in the normal incidence, but you get refracted rays away from the normal if you go from medium with higher refractive index to lower refractive index. As opposed in the opposite direction, you get refracted towards the normal. And very important phenomena with huge implications are that if we're going with the medium of higher refractive index to lower refractive index, you will have a certain critical angle after which there is a total internal reflection. So no light will escape from this medium into that medium. In the opposite direction, if we go from the, let's say, atmosphere into the ocean, this ray tracing applies as well. So it means that the entire hemispherical light is being squeezed into a range of directions that are contained within this critical angle. And mathematically, these things are really easily described by the so-called Snell's law of refractions, which basically is the n2 times sine theta 2 is equals n1 times sine theta 1. So knowing the refractive index, assuming that this is 1, this is 1.34, for example, for water, you can compute that this critical angle is about 48 degrees. And this is called Snell cone, everything that is here within this cone here, 48 degrees or so if we are in water. Yes, so if you're an observer underwater and looking up, you're seeing a bright cone of light and relatively dark background outside that cone. If the water was perfectly flat, calm, this would be a nice circle because it's wavy. Of course, it's kind of scattered image. Another phenomenon of refraction that you can observe, all of you are well familiar with. You can see underwater effects of under disturbed water surface. The refractive effects causes focusing of light. So waves act as lenses and create these bright patterns of bands sweeping across the bottom with very high intensities. And I don't know if you recognize this here background. I took this picture yesterday because it's actually the same effect as underwater is being created in air, but you don't see it unless you have some screen. So I noticed on one of the boats here in Ladar's port, a beautiful pattern of these caustics with a slightly undulated surface, a sunny day. This may be a meter and a half, maybe 2 meters, extremely bright bands of light being focused in air due to reflection this time on curved surfaces. Okay, so another phenomenon that is very important to realize it exists is referred to as dispersion. Dispersion is basically the dependence of the wave phase velocity on frequency or wavelength. So it does occur when light propagates from free space or atmosphere where dispersion is very weak to water. In water there's some dispersion where blue light refracts more than red light. So it basically refractive is a little bit higher in the blue than it's in the red. It also depends on salinity, temperature, pressure to some extent, but under constant physical conditions of temperature, salinity, and pressure, there is a wavelength dependence. So there is some degree of dispersion going on as well. For many applications, we actually do neglect dispersion. We assume one constant refractive index across the spectrum of interest to us. And yet another phenomenon that relates to wave nature of light is diffraction. This is something that you've probably observed sometimes. It's, for example, shown here. And it has been introduced by French physicist Augustin-Jean Fresnel. Basically, the light was found to have property to bend around the obstacles in a way, so it doesn't create behind the obstacle if you send a plane parallel wave. If you explain this in terms of wave description of light, you don't create a perfect shadow here. There's some intensity, measurable intensity of light behind that obstacle. And Fresnel used Huygens principle about this. For example, it can be diffraction can be observed behind the obstacle, or it can also be observed when you have an opening like this. Right? So it can be opening or obstacle diffraction happens. It's called Fermat principle, I guess. Yeah. How? Babinet principle. Yeah. Thank you. Babinet principle. Babinet principle. So regardless whether you have opening or obstacle, you get this effect. And so a nice explanation by Fresnel is, again, each point here generates these spherical wavelets and interference pattern. And if you have a screen here, you will see basically bright spot in the middle, then darker spots, brighter, and so on and so forth. Okay, so up to this point, I just covered several aspects and properties of radiation. I talked a little bit about dual nature of radiation, wave-like nature and particle-like nature. And right now I would like to talk a little bit about emission of light, where it comes from. So the primary source of radiation, and the source that we are concerned in ocean optics, is thermal radiation. And the main source of radiation that we are dealing with is sun. And in this case, but the thermal radiation is a very general phenomenon that occurs practically everywhere. Every body, every material medium, every body that material body that has a temperature higher than 0 is going to radiate energy. And this is associated with thermal motion of atoms and molecules within material media. And another major possibility for generating radiation is luminescence. There are many forms of luminescence, chemiluminescence, when chemical reaction leads to excitation of atoms to some higher energy, and then that energy is being emitted in the form of light. And we probably hear about some of this during this course, about one example of chemical luminescence is bioluminescence, which is produced by living organisms. Many of you probably heard it and probably seen it in the ocean. But for the most part here, we're going to talk a little bit more about thermal radiation now. So I already mentioned the name Max Planck, who at the beginning of 20th century was attempting to explain the observations of radiation from bodies, thermal radiation from bodies. And he was actually the first who introduced, when he was trying to explain the so-called black body radiation. It's a hypothetical body that under thermodynamic equilibrium achieves maximum absorptivity and emissivity, and it's in a perfect equilibrium, emission and absorption of radiation for such body. And Max Planck postulated that matter can gain or lose energy when interacts with radiation only in the small quantum amounts. So he did it before, actually, 1905 paper by Einstein, and he used this concept in his paper of black body radiation, and yet he's not credited with making an explanation that light has a quantum-like properties. But nevertheless, he used this concept to derive his black body radiations. What's of its form is written here, where you can see some physical constant, c squared, Max Planck's constant. This is the Boltzmann constant, but this is temperature in Kelvin and lambda to the power 5. So these are two variables in his black body radiation law. And it looks like this. Basically, this is some measure of intensity of radiation, magnitude, amount of energy being radiated versus wavelength for bodies at different temperatures. And you can see this function has this shape as asymmetric, sort of bell-like shape, but asymmetric. And the bodies with high temperature, 7,000 Kelvin, 6,000 Kelvin, tend to have maximum at shorter wavelengths. If you decrease temperature of the body, the maximum shifts towards longer wavelengths. But at the same time, the integral, so the total energy being emitted, also decreases. So each curve here is being described by Planck's black body radiation curve. But also you can see here two other important conclusions, or two other important laws that are being derived from, and were actually derived independently of Planck, but you can see them here when you put a series of Planck's curve, is the shift of maximum, lambda maximum, with decreasing temperature, and you also see the decrease of integral at total energy. And Stefan-Boltzmann law is basically states it relates to the total amount of energy being, this integrated energy being emitted by a body of a given temperature, Kelvin temperature, and it's described here as sigma to temperature to the 4th power, and it's called Stefan-Boltzmann law, Slovenian physicist, and his He was an advisor of Ludwig Boltzmann, actually. Ludwig Boltzmann was his PhD student. So this law is being credited to both of them. So very important, very strong dependence, yes? With 4th power of temperature. So that's what we see here. This integral is increasing rapidly under each curve if you increase temperature. And the location of the maximum was first described by Wilhelm Wien, who actually was also received Nobel Prize in 1911. He was an Austrian physicist. And it states basically that the lambda maximum, so that's the wavelength at which the Planck's curve peaks, is inversely proportional to temperature. And for temperatures on the order of 5800 Kelvin, 6000 Kelvin, which corresponds to the outer layers of the solar atmosphere, which is called photosphere. These are the outer layers of the sun. It's about 500 nanometers. Human body, about 37 degrees Celsius. We are emitting maximum emissions about 9,350 nanometers. Earth would be even shifted a little bit, surface of the Earth, somewhat lower temperatures. Not that much, but even further to the longer wavelengths. So everybody here, everything is emitting radiation. At these room temperatures, radiation is in the infrared. Okay, so let's talk a little bit. I have a series of slides about telling us that ocean optics, our research in ocean optics, is concerned actually with a relatively narrow range of electromagnetic spectrum. And why? There are a few reasons for that. And we're going to be concerned mostly throughout this course from range of the electromagnetic spectrum from near UV through visible to near infrared. So we're not going to be concerned with gamma rays or radio waves and things like that. So why is that? Okay, first thing is source of radiation is sun. And sun, the photosphere, solar photosphere is about 6,000 Kelvin. And this is the spectrum according to Planck's law. This is what is being produced by sun. This is now wavelength in microns. So we are here. This is 1 micron. So this is already infrared. So this is visible range somewhere here. So the peak of that curve is in the visible. But the sun produces a significant amount of UV radiation and a lot of infrared radiation as well. Now Earth, you can see, is about 300 Kelvin. It peaks over at wavelengths more than 10 microns and gets very, very low amount of energy in the near infrared. Okay, once the radiation is being produced by sun, is propagating through the free space and through the atmosphere. By the way, do you know how long it takes for radiation from sun to get to us? Anybody knows?
8 seconds.
How many?
8 seconds.
8? Yeah, about 8 seconds. Okay, so there is interaction. So it's about 150 million kilometers, right, with 300 kilometers per second. So there's, of course, two main processes when radiation goes through the medium, such as atmosphere, which consists of different atoms and molecules. There will be interactions between radiation, atoms, and molecules. These interactions will be in the form of scattering, when there will be a change of direction of propagation. And so it is shown here, for example, with atmospheric particles, atmospheric molecules. There also will be a possibility of interaction that ends with transfer of energy into matter. So the radiative energy is being absorbed and is being converted to other form of energy, such as heat or maybe chemical energy or something of that sort. And that's the process of absorption. And it can be selective, wavelength selective. Some wavelength going through some medium can go easily through, some may be absorbed. For example, you can see here an example with the different colors of light incident on the green leaf, and what's absorbed is the blue and red radiation, and the green radiation is being reflected or scattered from the leaf or transmitted. So the processes of scattering and absorption within the atmosphere will modify that spectrum of solar radiation in the following way. So this is the black body radiation. This is the idealized curve at about 5800 Kelvin. This is the actual measurement, the yellow thing at outside Earth atmosphere. And this is what would be at the red curve would be at the level of the Earth. So you can see different molecules have absorption bands, different regions of electromagnetic spectrum, and modify the spectrum. And also you can see very significant absorption in this portion of the spectrum by ozone. So the UV is effectively absorbed within the upper portion of the Earth atmosphere, mostly within the stratosphere. But still, what we have at the surface of the ocean, we still have a peak within the visible. Yes, most energy, maybe half of it, nearly half of it will be here, maybe 40 some percent within the visible, 400 to 700. There will be some percentage in the UV, and still significant percentage of solar energy is hitting ocean surface within the infrared region. If we take a closer look at solar spectrum at high elevation above the Earth atmosphere, we will actually see more detail. You could actually see that it looks sort of noisy, but it's the actual signal associated with absorption lines of atoms, molecules within the solar photosphere. These are called Fraunhofer lines. For example, here you can see sodium line, which is about 589 nanometers. So sodium atom has a capacity to absorb that at that wavelength of radiation very effectively. So you can see something like this if you have an instrument with very high spectral resolution. If you don't, this is going to be smooth. Okay, and now I have two plots here. So we are getting now to our point more and more transmittance. Again, transmittance in percent through the atmosphere versus wavelength. Now this is in microns, so we're going visible is just right here. This is 1 micron, 0, 2, 3, 4. This is infrared region. Different molecules in the atmosphere, water vapor, carbon dioxide, and so on and so forth. And here is a very important plot of very broad spectrum over many orders of magnitude in wavelength. The wavelength is in meters here, of absorption coefficient of water itself. So you can see, and this is also log scale. And you can see there is a very low absorption of water within a very narrow range, spectral range, which happens to be in the visible. So water is transparent, fairly transparent within that narrow range of electromagnetic radiation, and would absorb extremely strongly here and as well in this region. So okay, so atmosphere is quite transparent in this region, has some windows of transmittance there as well. It's opaque in some regions, as you can see. Water itself is transparent in this region. So if we combine the spectrum of light with the properties of atmosphere across the entire spectrum of where the meaningful radiation from sun is being emitted, with the properties of water itself, we come to the conclusion that ocean optics is primarily the science of radiation from near infrared from near UV to near infrared. And this is shown here, spectra again of wavelength in microns, 1 micron visible region. Dashed line is the black body, I believe 6000, and then you have realistic solid line is the outside the atmosphere, the radiation. This is now irradiance. I'm not so rigorous at this point of my lecture about actually talking what is on the vertical axis, but I think intuitively, I'm talking about some sort of measure of radiometric quantity. You will learn about it more. It's not that important right now at this point. In this case, it's irradiance in watts per meter square per nanometer. And you can see here, again, these atmospheric absorption bands. And when we get, so this is, again, one of these curves, the one that is at the surface is replotted here. And then you can see 1 centimeter below the surface of the water, 1 meter below the surface of the water, 10 meters, 100 meters. So you can see how quickly the near-infrared radiation is being absorbed within a very, very thin layer of water because of that behavior of the absorption coefficient here. Okay, I have 25 minutes to cover, now to talk a little bit more about mechanisms of scattering and absorption, and to give you some feeling about what happens in the microscopic scale, at the atomic and molecular scale, when light is being absorbed or when light is being scattered. So as we already touched upon these two manifestations of interactions of light and matter, scattering is change in the direction of propagation, and absorption is the conversion of radiative energy to other form of energy. Let's talk about absorption. Let's imagine here a model of a molecule that consists of several, first of all, let's talk about any generic hypothetical molecule that contains several forms of internal energy. One form of internal energy is referred to as electronic energy. It's associated with the distribution of electrons within the atom or molecule. Another form of energy is the so-called vibrational energy. It's associated with the vibrations of atoms within molecule. And finally, rotational energy is associated with the ways the molecule can rotate. All these types of internal energies possess the property that they are all quantized. They cannot change in a continuous manner. There is one form of energy that molecules and atoms have that they do change in continuous manner. It's the kinetic energy of the motion of molecules and atoms. But these three types of energies are quantized, so any atom or any molecule possesses only certain number of electronic levels of energy, vibrational levels of energy, and rotational levels of energy. These are the highest levels, and they correspond to, these are energies about 400 kilojoules per mole. And these energies tend to correspond to energies of photons in the UV and visible, perhaps near infrared as well, maybe 100 more or less to 1,000 nanometers. Vibrational levels of energy are smaller, and they correspond to wavelength of radiation in the infrared from about 1 to 20 microns. And rotational are even lower energies, and they're corresponding to much longer wavelengths. So now we are visualizing these all three types of energies in a molecule that has three electronic energy levels: ground state, electronic energy 1, electronic energy 2. Each electronic state also has a number of vibrational levels. These are these long lines, and rotational levels here, shorter lines. So these are the allowed transitions from one state to another state, yes, of energy for a molecule. Molecule can be in ground state at this vibrational state and maybe at this particular rotational state. It turns out that all the molecules here around us, almost all of them, practically all of them at these temperatures, are in ground state at these temperatures. Right. And there's the law, statistical law, it's Boltzmann, I believe, or Stefan-Boltzmann law, I think, that describes the statistics of how many molecules at a given temperature are at any given excitation level, if you can wish. So in fact, when temperature tends to zero, to absolute zero, without any changes in chemical makeup of some substance. All molecules and atoms within that substance tend to be in ground state. But in practical, at room temperatures, practically almost all of them are in ground state. The probability of finding something here and for the wall or something to be in excitation state is very, very low. If it was high, we would see that this wall would emit radiation, perhaps even visible radiation. Okay, so if a photon of appropriate wavelength and energy hits the molecule like this, what can happen? If that energy corresponds to some transition between ground state, electronics level 1, this molecule can get excited to a higher electronic level. And let's assume that this is maybe a very simplified model of chlorophyll molecule, yes, for the sake of discussion. So let's say that this chlorophyll molecule was hit by a blue photon and got excited to this higher energy level, electronic energy 1. And what happened then, very quickly, probably 10 to minus 11, 12 seconds, there will be loss, dissipation of that excitation energy to the lower electronic energy level. This is a very, very effective process, this dissipation into heat. You can also see through this diagram that electronic levels can be close to one another, relatively close to one another, in a sense that each electronic level has several vibrational, rotational levels that can even overlap with each other. That's very important because that can give us the measure that when we observe the phenomena of absorption or emission, then can be nearly continuous as a function of wavelength, just because of multiplicity and overlap between very many these discrete levels of rotational and vibrational levels associated with different electronic levels. So in any event, let's say chlorophyll molecule end up very shortly in the lower electronic level 2. And this actually tends this distance from here to there corresponds to energy of a red photon. So what can happen when the molecule ends up here? It can do several things. One thing is the energy can be dissipated into heat. Again, so the energy will be dissipated in the heat, so it will be distributed between many different molecules, and eventually will end up in the will be in a thermal motion, and the molecule will end up back in the ground state. From this state, there are also two other pathways of utilizing that excitation energy. One is this energy can be channeled to drive the photosynthesis, so that here we will create a chemical energy that will correspond to that amount of energy. Or we can see the emission of the photon from this level, electronic level, back to the ground level, and that's the fluorescence. Some of you study fluorescence. We've heard it today in the morning, so that's the chlorophyll fluorescence. So it can happen only here from that lower electronic energy level to down back to the ground state. So this is this more or less corresponds to the SORAD band, so-called blue band of chlorophyll, the major band, absorption band. This corresponds to the red band. Of course, the red photons can also be absorbed, can also be utilized to drive photosynthesis, and energy can be dissipated through heat or can be converted to fluorescence. So this is an example of conceptual description of the mechanism of absorption. Yes. So the bottom line is this. So we can absorb energy within this spectral band through electronic transitions within molecules or atoms, in the infrared through vibrational changes in vibrational states, and even at longer wavelengths, the absorption will be through rotational. And the emission is basically the opposite process. So the thermal emission of bodies room temperature are associated with the transitions here, rotational and vibrational transition. That's what happens here. Infrared radiation is being emitted. through these transitions, but the downwards, yes? Downwards. Absorption, upwards. You have an example, I put here an example of spectra, absorption spectra of Planck pigments. Okay, I think we'll see this many times, or at least later on as well, so I'm not going to stop at this. Water molecule itself, it's the most abundant molecule in the ocean, of course, so it's very important to say a few words about what happens when water molecules interact with incident radiation. The primary phenomena that are responsible for this steep rise of absorption curve for water molecules are these different kinds of vibrations, a symmetric stretch, so it's something like this, asymmetric stretch, or bending of the molecule, hydrogen, oxygen. The other way around, yes? So this is again absorption spectrum with the minimum in the visible, and these are the vibrational and eventually rotational spectra of water molecule. Oh, this is electronic transitions, yes? So here, if you are in high energy portion of the spectrum, it has to be associated with electronic transitions. And here, just put examples for several atmospheric gases, how they absorb, but this is visible portion of the spectrum. Not much is going on, really. A lot of stuff is going on in infrared and in the UV. And it's actually very fortunate for us that there's a lot of absorption going of this high energy UV through ozone. Okay, so that was mechanism of absorption, and I have a series of slides about scattering. So scattering is the change of direction of photon propagation, of wave propagation, whatever we like. And and it always happens when radiation is going through material medium, always. Any medium that contains atoms and molecules have some sort of inhomogeneities, and even individual electron on atom is something like this. It's an object that will cause scattering, and not always it will be significant and strong enough to be measurable, but it always happens. So whenever the radiation interacts with atoms, molecules, there will be some sort of redirection of portion of radiation in different directions. And one of the most simple, elegant ways of explaining why radiation is being scattered or redirected, if you wish, is this model mechanism that involves the oscillating dipole. So imagine a very simple atom that consists of one positive charge and negative charge. And imagine now that we are sending this, and this is referred to as dipole. And it has certain dipole moment, which is the charge times the distance between these positive and negative charges. But imagine that we are sending now electric field is incident on that pair of charges. So charges will experience force, yes? A force associated with the incident electric field, but that electric field varies very quickly. So in response to that incident field, the charges will start to move also. And it turns out that that's not easy to read. So this is negative charge, positive charge. What I'm trying to say, as the different phases of the incident field go through this pair of charges, they are forced to move. And in reality, electrons will respond much more significantly than heavy protons, if you wish. So electrons will move rapidly in response to the incident electric field. These motions are very tiny, fractions of the size of the atom, very small fraction, but they are there. So electrons are moving in response to incident field, and we know we can go back to Maxwell equations. Time varying. So this moving charge will create its own field, secondary field. And it will change over time. So it will change a time varying electric field. And according to Maxwell equations, time-varying electric field is going to generate time-varying magnetic field. So this oscillating dipole is creating its own secondary electromagnetic field surrounding it and spreading into the space around. This is scattering. This is why you see everything here surrounding us. Yes, this is why you see this surface. This is why you see me, because some light coming from lamps and scatters out of these surfaces. And this is the most fundamental phenomenon, what happens at the microscopic level. Now, during this process of scattering, the radiation, the secondary radiation being produced is most often with no change in wavelength. And that is referred to as elastic scattering. This may be a little bit, I would say, misleading in a sense that I have these lines perhaps suggesting that these are the true energy levels of molecule. I mean, there's nothing, when scattering happens, there's nothing like when absorption, that atom or molecule jumps into some other specific discrete of internal energy level, and then dissipation to heat may occur, or fluorescence, or chemical reaction, something. No. This process happens at any wavelength, and any wavelength, this dipole responds at some wavelengths or frequency of incident radiation. The dipole will respond more strongly than in others. That's why scattering can be wavelength dependent, and it is generally. But the scattered field, if we, let's say, send hypothetical monochromatic wave, which doesn't exist, we'll never produce it, but let's assume it for the sake of our discussion, monochromatic field incident of a given wavelength. So the dipole is sending secondary field of the same wavelength. That's elastic scattering. But what's very important, and also especially in the ocean, in ocean optics, is that not only elastic scattering occurs, it's a ubiquitous process. It occurs on water molecules. It's produced by particles. Very many types of particles and water molecules. But there's also inelastic scattering process being produced in the ocean, and it is associated with slight changes in energy of water molecules. Water molecules themselves can gain a little bit of vibration energy during this interaction, and the scattered field will be produced at a longer wavelength than the incident field. And this shift, this is called Raman scattering, after Indian physicist Raman, 1920s, I believe, late 20s, I think. Actually, that thing has been also discovered almost simultaneously by, if not simultaneously, but some Russian physicists. But this discovery is being credited in the Western literature to Raman, in the Russian literature, not just to Raman. But this transition, where there's some gain of energy, internal energy within molecule, is referred to as Stokes-Raman scattering. It occurs at typical environmental temperature. It could be also this kind of inelastic type of scattering, Raman anti-Stokes-Raman scattering, but doesn't happen in the ocean. This shift is on the order of a few tenths of several tenths of nanometers for water molecules. So let's say you can, this could be like 400 nanometers, and Raman scattered light 440 or something like this.
Yeah, so maybe 450 or 60.
Or 450, 60. Yeah, so something like that. And it occurs continuously across the entire spectrum. Yes. Just like elastic scattering, continuous across the spectrum. But one important thing is that if you, let's say we would send red light, orange light, green light, and shorter blue and violet light, UV light on something like a water dipole, this oscillating dipole. And the willingness of this dipole to oscillate in response to the field depends on the incident radiation. And the shorter it is, the more energetic incident radiation, generally you generate much larger vibrations of the dipole. This is why you are generating a stronger scattered field. And so an important consequence of this is, which I will show in a moment, is that For example, why sky is blue, and because these molecules scatter more blue light than red light. Okay, so a few other things about scattering. Let's say we have this hypothetical dipole, negative and positive charge, sitting somewhere, and we are sending electromagnetic wave. So at any given instant of time, this dipole, these two charges, will experience a given phase of the incident field. But if we have a larger object, which is comparable to wavelength of incident light, or let's say phytoplankton cell or some mineral particle that has a few microns, okay, different portions of this cell will experience different phases of incident field. And of course, there are plenty of atoms here, and these charges, they will respond accordingly, right, to different phases. So this is going to create quite a bit of complexity in scattering patterns, as opposed to something like this that is easier to predict and has well-described properties. So, so if we have a larger object, we can conceptually subdivide it into very many dipoles. And let's say we imagine plane parallel wave, incident wave, illuminating an object consisting maybe of millions of dipoles, and each of these dipoles is generating its own scattered field, and we are observing and with some detector maybe at that scattering angle defined as the angle between primary beam, unscattered beam, and the direction of scattered beam. And basically what we have to do, we have to do a very rigorous summation, including interference, including the differences of phases of the individual wavelengths. So we have to add up each wave, scattered wave, and account for the phase to get a scattered field produced by a particle consisting of subdivided into very many conceptual dipoles being in that oscillatory motion and creating their own scattered fields. And this is just an example of, we are going back to some, this double slit experiment. There is similarity in this. Two spherical waves, this could be two dipoles within a particle, yes? That are generating scattered fields, and they interfere and produce this interference pattern. One way of, I have 1 minute, so not that many slides left, so it's not so bad. I can finish on Wednesday with a few more slides. But here is the description of, I should have said that there are rigorous ways of solving this problem. They were solved at the beginning of 20th centuries when you sent plane parallel wave, and you can solve electromagnetic equations of Maxwell for scattered field at different directions for objects that have spherical shape and are homogeneous inside. When they are non-spherical and all these dipoles are different, so the chemical makeup here is different internally, that problem becomes very difficult. But there is so-called discrete dipole approximation approach that you can actually take an object of arbitrary shape, an arbitrary internal distribution of okay, I have to say it, refractive index inside, or polarizability, if you wish. Polarizability is another way of linking, is a property of material that is linked to refractive index. One interpretation of refractive index was phase velocity. Polarizability, or willingness of this guy to oscillate in response to a given incident field. The polarizability of this guy can be different than this guy if this is a different chemical molecule. And it will have different refractive index. So that's another way. So willingness, in other words, of willingness of the dipole to oscillate in response to the field is also linked to refractive index. So anyway, discrete dipole approximation, you can divide your object of a given shape to very many dipoles and assign values of refractive index or polarizability to each of it and solve it. Very cumbersome, very difficult mathematically. I don't know if these solutions exist for particles that are like 10 or 20 micron in size. I've seen some for a few microns in size, maybe some micron range. It's computationally a very difficult problem, but can be done. So I think I stop at this point, and I have probably 5 slides, so I will continue to close this lecture on Wednesday. Thank you for your attention.